Hello and welcome. In this video, I will be covering count sort, which is another interesting sorting algorithm. And yes, this is a sorting algorithm with linear time complexity. But there's a catch. It does not work with any inputs. It's a very easy algorithm to understand. And one of the main points over here is, let's say if I know how many people are there ahead of me in the queue, then I can easily find what's my position and go and stand in the right order. Let's look at an example and see how does count sort work. An example with the integers. Here you see I have one array with some repeating numbers. There are some duplicates, and I'll be writing down the frequency of each number over here in this particular array. So the way count sort works is it starts the algorithm by counting the number of times each input is appeared or each element has appeared in the array. For example, here if I see how many times 7 has appeared, what I'm going to do is in this array, which is like a hash map for me, where the actual number 7 is a key, and the value inside here would be the frequency of this number. That means how many times it has appeared in the array. Here it appears 2 times, so I have made this um, counter as 2. Let's do it for rest of the numbers. I'll be going from left to right over here, and I will be just counting these numbers and put the frequency in this array. For 2 again it's 2 times. Okay, 1 also appears 2 times, and 3 appears 2 times, and 8 appears once, 0 appears 1 time, and rest all are 0, which is by default. Okay, now what have we gained by building this frequency counter? We know how many times each element repeats itself. Now before I move on to the next step, cumulative frequency, there is one more concept that is associated with count sort, that's called stability or stable sort algorithm. In such algorithms, what we also want to do is we want to preserve the order of equal elements. uh, like if you see, there are two twos uh, at index number 2 and index number 3. In a normal circumstance where I just want a sorted list of these numbers, it does not matter whichever 2 appears first. But in certain cases, I may want to preserve this order and just keep this. Consider that if this 2 is just a key of certain larger object, okay, and I want to preserve that order, whichever came first, I want to place that first over here in my final array. So that stability is preserved in certain way that we will talk about later. This is a concept that's associated generally with the count sort algorithm and other stable sort algorithms. However, if we just want to sort these numbers, it does not matter. We can safely ignore that for now. So let's go to the next step, which is now counting the cumulative frequency. Why are we doing this? Why are we calculating cumulative frequency? As I told earlier during this video, that if I know how many people are before me in the queue, then I can easily go and find out what's my current position and go and stand over there. So when we find this cumulative frequency, we allow each number to identify where does it end in a queue. Okay, let's say right now we just have the frequencies, but we don't know where exactly 2 will appear. This is a natural sequence for these integers. Hence I already know, like if there is a 5, it has to come after 4, but I don't know how many 4s will be there, or how many 3 or 2 or 1 will be there. That's why I cannot exactly say that whether 5 will appear at position 5, 6, 7, 8, 9. Now let's build the cumulative frequency counter. Let's start from the first element. We have 1, so it's remains 1, and we just add the current frequency to the previous element. It becomes 3, 5, 7, remains 7, 7, 7, 9, 10, and now what do we do with this cumulative frequency? This cumulative frequency will tell which is the position where this particular number is ending in the queue. Okay, and when I spoke about stability and preserving the sequence of um, numbers as they appear in the original one, that's why we want to prefer and start from the reverse of this array, the original array, instead of starting from the first. Even if we start from the left hand side of this array, it would still end up giving us a sorted array. But what might happen is we might reverse the order of these repeating numbers. The second 7 would become the first 7 in the final array, and vice versa. So let's just go with the reverse order for now and preserve the original sequence of these numbers as well. What I'm going to do is I'm going to start from 9 here, and let's look at the 0. Let's pick this number 0, and let's see in the cumulative frequency counter where is the 0. Okay, so if I look at the 0th index, what does it tell? It tells me 1. Now what I am going to do is I will take this number, okay, and I will subtract 1 from it. 1 minus 1, and I will get what is the index where I have to write this number. Okay, so it gives me 0. I go and write 0 over here. Now I move to 8 and see where does 8 end in the cumulative frequency counter, and this says 10. Okay, now what I am going to do is I am going to subtract 1 from here. 10 minus 1, which is 9, and I have to go and write 8 over here. So that's the position of 8. I have to do the same thing for rest of the numbers. Let's just do that quickly. 3, and let's look at where does 3 appear here in the cumulative frequency counter. 7. I need to subtract 1 from here. Okay, basically what this is saying is that 3 must appear at the 7th position in this array. So if I have to find the 7th position, then since the array starts from 0th index, that's why I'm just subtracting 1 from here. Okay, and now I go and write 3 at 6, index number 6. So every time I am reading from here, I am also subtracting 1, and this value will be overwritten. Like instead of 7, it will be 6 now, and instead of 10, it will be 9 here. Okay, and instead of 1, it will be updated back to 0. Okay, and at 6th position, let's go and write 3. So we have put 0, we have copied this 8, we have also copied this 3. Now again I will go and do same thing. I will check in the cumulative frequency counter where should this 3 appear. Now what I am able to do with this, just look at this thing, that even though both the numbers are equal, it shouldn't have mattered which 3 appears first, but since I am starting from reverse, it will preserve the order. Now I am picking up the first 3, and it will automatically come before the second 3 that was appearing at the index number 7 in the original array. So now it is 6 minus 1, and it is supposed to go at position 5. Let me update it over here, my cumulative frequency, and just go and write 3 over here. Okay, now for 1, let's see what is there at index number 1 in my cumulative frequency. It's here 3, and I will do 3 minus 1, 2, and let me just go and write 1 over here. Okay. And I will also update this value. Now again, I move to index number 4 in my original array, and let me see what is there at index number 1. Okay, so again this 2, I need to subtract 1, 2 minus 1, and then I will go and place my number at position number 1. So even this is done. Now let's come to 2 and see what is at the index number 2 in my cumulative frequency counter. 5, so 2 must appear at the 5th position. To find that corresponding index, I just subtract 1, which gives me 4. I update this over here, and I also write 2 at the 4th index. Same, again I will subtract 1, I will get index number 3, and I will write 2 here. So we have covered this 2 also. Now there are 2 7. I will just quickly write them. At index number 7 I have 9, so first it will give me the index number 8 to fill the position. Then again there is 7, it will give me an index number of 7. So first 7 goes at 8th index, and then second this. Now the first 7, or 7 that is at the 0th index in my original array, comes at the index number 7 over here. Now if you look at this array, this is in a sorted form, and that's all for the count sort. It's fairly simple algorithm, and the only caveat here is that it works on a range bound inputs. Now let's quickly do an implementation in JavaScript. Let's begin by writing function count sort. Let me accept the array, and I will also accept the range in form of min and max. Let's just take the range between 0 to 9 as our example. I could have taken it as an array like or min max, or even figure out by finding what's the minimum and maximum value in the array. That's totally up to you. Okay, now the first step is to build the frequency counter. For that, let me take an array and call it frequency, or just call it freq. Okay. Now I have to go from min to max. Let I equals to min, and it's less than equal to max. Okay, I is less than equal to max, and I plus plus. Now what I am going to do is I am going to initialize every element by 0. Okay. So this is just the initialization of my frequency array. Now I will be doing an actual frequency count by iterating over my original array. This is building frequency count. Here I am just initializing everything by 0, and then I am actually counting the frequency. Now what I have to do is build the cumulative frequency. This is so that we can figure out where does each element appear in the array in the final sorted position. And here I can start from index number 1, because I will be just adding whatever is in the previous index to the current index. Frequency I equals to in the previous index. That's all. Now this is the final step. Build the sorted array. Let's take another new array and call it sorted ARR. Let's go over the original array in the reverse order so that we can preserve the original sequence of even the same elements. Now let's just take few temporary variables for the sake of clarity. Current element equals to ARR of I. Okay. Now I'm going to find its position in the array. Position equals to, I am taking from the cumulative frequency, and I have to subtract 1 from here, because cumulative frequency will give the position where this element should appear. But since our arrays start from 0th index, I am subtracting 1 from it. Element in the sorted array at the position POS, and the element is current element. And then I have to also reduce the my frequency counter, okay, by 1, so that whenever the next element is found of same value, then we can find its correct position and not override the previous one. That's all. Let's test it out with the same example that I used during the dry run. 0 1 1 2 2 3 3 7 8. That's in the sorted order. That's all. It's quite simple and easy to implement algorithm. Thanks for watching.